the psi on both sides can be eliminated. And then the energy is minus h bar square over 2m plus k square. Okay? And you put the boundary conditions at the edge of the box here. The wave equation is not going to be defined at the edge because it's inside the box. So the a plus b is equal to 0, which means b should be minus a, and a e to the I kl minus a e to the minus I kl. Or the Euler theorem, it is nothing but 2 sine kl right? Then it should be 0. So k is equal to n over L x. Now we see that the wave number is quantized, where n is equal to 1, 2, 3, 4, multiple integers, right? So the n cannot have the fraction between these digits. So it is quantized somehow. It does have forbidden energies, forbidden wave numbers. So you put that thing into the wave equations, then psi n now is equal to c n sine L n pi x. Okay? Then this is the eigenfunction. Then eigenvalue now, that is going to be h bar over 2m. Now k square, that is equal to the m pi square. And then that is n square, okay? And then h bar square pi square over 2m times 1 over L. That is the physical dimension. L. So the energy is going to be quantized in this fashion. This is the eigenvalues. In order to get this C at the constant, we have to set the normalization of the functions. Then we can set this Cn value. Like if you integrate from x equal to 0 to L, as far as the electron is confined in a box, then the probability of finding a particle inside this box should be 1, right? So Cn square sine Ln pi x dx, that is going to be 1, and then that is 2 Cn square 1 minus cosine L 2n pi x dx. And we know this integration, so that C now Cn is square root of L over 2. There is a normalization factor to make the psi as a probability of finding a particle. The probability should be 1. right? So we have eigenfunction and eigenvalues so that we can find the n and eigenvalues En, the energy state, the functions, wave functions, and the probability of finding a particle for that quantized states. Now, the ground state is n equal to 1. That is the ground state. So n cannot be 0, because 0 means nothing and is trivial answer. Now, when n equal to 1, the energy level is going to be represented with this. And the wave equation is something like this, so that when 0 to L, this wave equations look like this. And the probability of finding a particle that is something like this, and that is going to be exactly the same to this, right? And this maximum value corresponding to 2 over L, something like this. All right? Now, what happens in a second excited state? The energy level is going to be 4 times ml squared, and then this wave function is going to look like this, and the probability of finding a particle like this. What does this mean? It means that at the center, the electron is not going to be at the center in the excited states. It's amazing. It's a different interpretation. This is not what expected. In a classical theory, no matter what, the electron is excited or not, it's a ground state. The finding a particle, the probability of finding a particle is equal, and everywhere is going to be 1 over L, something like that. But in a quantum analysis, we just found that when it's excited, the first excited state, the particle is not going to be at the center. That is amazing. What happens if we excited more? Then the energy state is 9 times h bar square pi square to m L square, and then the wave equation is going to look like this. And then the probability of finding a particle now is going to be something like this. And 1/3 and 2/3, there's no chance for the electron be there. That is a new findings, and then there is a very unexpected thing, right? What happens if you excite more and more? Then the wave equation now becomes the probability going to just divide it in many nodes, something like this. This is the probability thing. And then this is 0 to L. And then here, that is a 2 over L. Okay? That is what we expected in the classical theory. And we call that the correspondence principle. means when n gets infinity, the quantum analysis should approach to the classical theory. Okay? That is the correspondence principle. Classical expectations. If when it is highly excited, the quantum analysis does not approach it to the classical theory, then there's something wrong happens in the quantum theory. Quantum theory just says that when most of the cases that we do see in the substance, it is a very much excited state, so that the we expect the probability of finding a particle inside a box is just nothing but an O2 over L, because it is the dimension is L. But in a quantum analysis, that is very highly excited state, that is right. But when it is approaching to the ground state, then we are going to have a different probability of finding a particle as we expected from what we expected. Like in a ground state, the particle is most probably at the center. But when it is excited means that absorption of the energies from outside, then the probability is finding a particle at the center is going to be 0. That is a new findings. And if you talk about the energies state here, we can see more astonishing thing. Like the ground state energy level is here, E1, and that is h bar square pi square over 2ml square, right? So if you set this thing as like, let's say x, okay? Then the ground state is, the energy state is x 1 over L square, right? Now, the next energy state is going to be 4x 1 over L square, right? And then the next one, E3, is 9x 1 over L square. And then the fourth excited state is going to be 16x 1 over L square, something like that. So that the gap is proportional to the n square. And this dimension is proportional to the L square, 1 over L square. Now, when we talk about the dimension, 0 to L, if it is in a centimeter orders, okay, in a centimeter orders, then this L is the gap between the energies is not much. But when you reduce the L in an atomic size, like angstrom, 10 to the minus 8 centimeters, then the gap is going to be 10 to minus 16, L squared is going to be 10 to the 16, so that 1 over L is now going to be 10 to the 16th. So that this energy gap is going to be very huge, right? When it is excited more highly, then the energy gap here is something times 10 to 16, so that it's really, really big. And this energy gap means in between these two, there is no available eigenvalues. What does that mean? There's no energy. allowed for the electrons. So when you excite the electrons, free electrons, captured inside a box, you excite that very high energies, and then you just suddenly cut the energies. Then this electron has to return to the next available energies. It has to return to the next available energies. Right? And then this huge energy is going to be emitted to the outside. That is the X-rays. So when you have a metal, this just predict this just says that the Schrödinger equation just says that when you have a copper, for example, that is a metal. Inside the copper, you have a lot of free electrons. And this free electrons is captured inside this box. The electrons is not going to be out of this metal solid, right? And you apply high electric field so that the electrons here is going to be excited to the high energy levels, the electron independent one electrons. And then you cut down the energies, electric field, then this excited electron is going to return to the next available energies, and then the gap between the energies is huge, like something times 10 to the 16th, right? Then it has to emit the X-rays. That's how we can get the X-rays, and then that is why we can expect the high energies. So you can see that the classical view and the quantum view, classical view, the probability of finding a particle captured inside a box is equal. That is the classical view. But in a quantum view, the probability is a function of the excited states. It's different from the excited states, depending on the excited states. And in the classical view, every energy is available for the electrons. But in a quantum view, the energy gap is going to be huge when you decrease the dimensions to the atomic level, like a quantum well. Quantum well means you decrease the size, you capture one free electrons inside the well, of which dimension is just atomic levels. Then that electron is going to be excited with the outer electric field, and it's going to emit energies. And that is the one way to understand the lasers that you can have in a solid state. Right? So you can have a reflection, a transmission, and tunneling of electron waves in you can understand those phenomena. Reflection and transmission and the tunneling of electron waves. Okay, you can understand this reflection, transmission, and tunneling thing if you look the electron as a wave, say the matter wave or electron wave. And then that has been described in the text. So you just read it, and we are not going to discuss about this in the class. But I want to read carefully about the tunneling phenomenon among these three, because this tunneling cannot be expected from the particle view, classical view. You cannot understand the tunneling thing. But only when you understand the electrons as a wave, then you can see this phenomenon. The tunneling is nothing but the potential energies is outside this wall. This potential energy is zero, and then here it has a certain potential. V naught, supposedly it should be large, and electrons coming through here. Then when this dimension, this x is small, okay, this electron can propagate across this wall, which is tunneling. In a classical view, as far as the V naught is larger than the electron energies, it never can do tunneling in this situation. But in a quantum view, you begin to understand that even though the electron energy is less than the V naught here, the barrier, it can somehow the probability for the tunneling. So you read that in the text, but when you read the tunneling, that is the most important thing, applying the Schrödinger equations in there. Okay, Wednesday, we are going to talk about the linear harmonic oscillator and the hydrogenic atoms. All right? Okay. And on Wednesday, I'm going to give you the homework again. And then I think on Wednesday, I can give you back the answers of the first homework and then grades. All right? 희재, 맞지?